I think it did, maybe. Yeah, it started it. Good. That's the shortcut way to do it. All right. A few more problems. This is one of the ones from Monday that I didn't finish, and it's not a bad example of a problem. Actually, we have a ring of radius r with a total charge q spread evenly over its perimeter. What is the potential difference between the point at the center of the ring and a point on the axis of the ring, a distance 2r from the center of the ring? So I think first, just for an example, I'm going to do a simpler problem. And imagine that we just have a circular ring and we're going to calculate the potential at the center of it. We'll imagine that it has a total charge Q on it. And so there's our ring of radius capital R and total charge Q. And we want to know the potential right here at the center of it. Okay, well, I'm going to figure out a charge per unit length on this thing just for the heck of it. And lambda will end up equaling that Q divided by the circumference of it, which is just 2 pi capital R. And then I'll use little tiny segments of this thing and add them up, and I think I'll maybe integrate in a clockwise direction, and I'll start here and just integrate all the way around the entire circle here. And so at some point, I'll be taking into account the charge of a little bit of the circle here. And this little bit of the circle will have a length. This is going to be capital R. This will be d theta. And so the length of this little tiny arc will be r d theta. And the electric potential due to that, I can think of it as being dV, is going to be lambda times, oops, well, I'll stick it on here, times r d theta. That'll be dq, and I want to multiply that by k sub e, the electrical constant, and divide by the distance away that it happens to be, which is actually capital R in this case. So, well, if those divide out, they divide out. Oh, I've got a lambda in the or an R in the charge there as well. So that'll keep me honest. Anyway, the dV, little amount of potential, then is going to be, if I write it in a better order, k sub e lambda d theta, and that doesn't look so bad to calculate. Let's see, the V is going to be what I get if I integrate. By the way, this is assuming when I use an expression like this, where it's k sub e dq over r, that's with the assumption that the potential at infinity would be 0. So that expression works there. We can't always use that, but we can here. Anyway, I'll be doing the integral of k sub e lambda d theta, and what I end up getting here is k sub e and lambda come out. I'll be integrating from 0 to 2 pi, and so v will equal k sub e lambda times the integral from 0 to 2 pi of d theta, which is just 2 pi. So it'll equal 2 pi times k sub e lambda. That's the potential at the center of this thing, but then lambda is q over 2 pi r. So V ends up equaling 2 pi k sub e times q divided by 2 pi capital R. The 2 pi's go away, and I end up with the potential is k sub e q over r. That's like the potential of a point charge that is a distance r away, or that you're a distance r away from. But in this case, it's a charge of q that's spread evenly over the circumference of this thing. And it's as if it's all concentrated at one point, but it's little itty bits that all add up together, but they don't add up as vectors. They just add up as scalars. So it's not such a bad problem. Now, what about on the axis of a ring, if we're going to be doing something like that? Well, we might be able to do something similar here. Let's see. I'll try another sketch and look at the geometry of a ring of charge there. So here, I'll just draw a line that'll represent the axis of the thing. And then at one end, here's the ring of charge of radius r. And again, it's got a total charge q on it. And it's just like the previous part. Lambda will equal capital Q over 2 pi capital R. But let's figure out the potential at a distance out here, x. And then for this problem, we're going to let x equal 2r, but we'll deal with that later. And figure out what the potential at this point happens to be. Well, I have to integrate over the charge distribution again. The distance from this point, this can be point P, I guess, from to any little chunk of the ring is going to be, this will be the square root of r squared plus x squared. In this case, x isn't really a variable, although I can vary it once I'm done doing the calculation. But what I integrate over is over the charge distribution. And the potential is going to equal the integral over the charge distribution of k sub e, I'll write it k sub e dq over the distance to that thing, which is capital R squared plus x squared. And for the purposes, well, for the integration, x is a constant. We're always staying out here at the same point. R is a constant, k sub e is a constant, and I end up with just getting, whoops, k sub e and the square root of r squared plus x squared come out of there. And the integral is just over the charge distribution dq. Well, if I integrate over the whole thing, I end up with capital Q. For that, I don't even have to use lambda on this. And so I end up with, in this case, the potential out here at a point P is going to be k sub e capital Q divided by the square root of r squared plus x squared. This is like as if it was a point charge, but this one is a distance r squared plus x squared away from us. And very similar to what we had here at the center. In fact, if x is 0, this expression becomes this expression. And so that's all there is to it. Well, let's go and look at that problem again in light of what we just figured out. A ring of radius r with a total charge q spread uniformly over its perimeter. What's the potential difference between the point at the center of the ring and a point on the axis of the ring, a distance 2r from the center of the ring? Well, we already figured out at the center that V is equal to K sub E capital Q over capital R. At X away from the center, we have the potential is K sub E Q over the square root of X squared plus R squared. And if X is equals 2R, I just have to plug in a 2R for X there, and the potential will be K sub E capital Q over the square root of 2 capital R squared plus R squared under that radical. And let's see, that will equal K sub E Q over, this would be 5R squared under the radical. But I can rewrite that. I can factor out the R squared as an R, and I'd get K sub E Q times the square root of 5 times an R, which is not under the radical anymore. So that's what it is at that point. And the delta V, I'll call this V sub C and this V of 2R. V from at the center minus V of 2R. This will be the potential difference that we're asked to find, is going to be K sub E Q over capital R minus K sub E Q over the square root of 5 times capital R. And I can actually factor out most of this thing, and I get K sub E Q over capital R times 1 minus 1 over the square root of 5. And if you prefer your denominators to be rationalized, you could write that as K sub E Q over R times, oh, let's see, square root of 5 over 5. So it'll be 1 minus the square root of 5 over 5, which could be written as 5 minus the square root of 5 over 5, or I don't care. Or you could actually calculate out what that thing happens to be. But that's one. We're figured out the potential at the center, figured out the potential at a point distance X away from the center on the axis, and then just substituted in that 2R for X and figured out the potential difference. So not too bad a problem. Okay. The x-axis, here's the last problem here. The x-axis is the axis of symmetry, is the symmetry axis of a uniformly charged ring of radius r and charge q, just like what we were dealing with. The point charge, capital Q, of mass m is located at the center of the ring. So it's the same amount of charge, but we've got it there at the center. When it is displaced slightly, the point charge accelerates along the x-axis to infinity and beyond, presumably. Show that the ultimate speed of the point charge is, and this is what we get. Well, let's figure out the potential difference between the center of the ring and the point at infinity. And actually, at the center of the ring, at center. We already figured this out. V is going to be, now this is the potential, not the potential energy of that charge yet, but it's just going to be that thing we figured out. K sub E, capital Q, over R, and that's what we have there. All right. At infinity, the potential will equal K sub E Q over the square root of, remember, x squared plus r squared, but in this case, it's going to be infinity squared plus r squared, and that's equal to 0. So there's no potential energy. So the potential difference between the center, this is V at the center, and the potential at infinity is going to be just this thing. Delta V is going to equal K sub E Q over R. And that's if we take the value at the center minus the value at infinity. If we did it the other way, it'd be minus K sub E Q over R. Well, we displace it just slightly and let the thing go. Oh, the potential energy change. This would be delta U in going from the center to infinity is going to be Q delta V, which is going to be K sub E Q squared over capital R. So that's and in this case, this is actually the amount of potential energy that the charge loses as it goes from the center to infinity. The potential energy it loses, but it gains kinetic energy. Now, how could we write that nicely? We could say, treat it as a conservation of energy problem. We can say that U initial plus KE initial is going to equal U final plus KE final. Well, U final is 0. This is out at infinity. That's 0. Kinetic energy, it says it's displaced slightly, but it isn't really given a shove of much. It's just pushed the tiniest little bit away from that center. And once that happens, it'll be repulsed by that ring and pushed away. But the kinetic energy, initial kinetic energy, is also 0. Well, the final kinetic energy is going to equal the initial electric potential energy. So the initial electric potential energy is going to be K sub E Q squared over R. And the final kinetic energy is going to equal 1/2 mv final squared. Oops, it says the mass is capital M, not little m. All right, well, let's just solve this thing. Multiply by 2, divide by m, and I would get v final squared is equal to 2k sub e q squared. I'm dividing by capital M, and I already had an r down there, so I've got that. And the v final is just the square root of that, like I was supposed to show. 2k sub e q squared over capital M R. So this is playing around with these ideas a little bit. Okay, the set of problems I've got for today are some that I kind of reserved for the last day of this topic. They're more challenging, but a couple of them are kind of interesting applications, and like to do those. Start here. We have a very long wire carries a uniform linear charge density lambda. Using a voltmeter to measure potential difference, you find that when one probe of the meter is placed 2.50 centimeters from the wire and the other is 1 centimeter farther, which would make it 3.50 centimeters from the wire, the meter reads 575 volts. Now, something they didn't tell me is if this is a positive charge density or a negative charge density. They also didn't say which probe of the meter they put closer to the wire and which they put farther away. And so we don't necessarily know from what we're given. We won't be able to tell if it's a positive or a negative charge density on the wire, but we should be able to figure out the absolute value. And I'm just going to do something where I'll assume that the charge density is positive, and if I had more information, I could nail it down, but I'll just live with that. Okay, well, something about a long straight line is that, for one thing, its electric field is going to point, if it's positively charged, its electric field will point radially away from the wire. And so looking down the wire, you would have this electric field that just points away. Now, this is looking down the wire. This is not spherical. So it's, if we looked in other dimensions, we wouldn't get that idea. But if you look down on the wire in the plane, say the wire's, I don't know, lying there somewhere, in the plane of that thing, the electric field is going to be pointing away, and it'll have the same value everywhere if it's a very long wire. Okay, well, back in a previous unit, we actually developed the expression for the electric field of a wire like this, and you can write it a couple of ways. The electric field is equal to lambda over 2 pi epsilon naught r. Oops, we're missing a case of E here, I think. Oh, no, we're not. That's encased in this. If you multiply the top and the bottom of this by 2, you get a 4 pi epsilon naught on the bottom, and 1 over 4 pi epsilon naught is k sub E. So you could also write this as 2 k sub E lambda over r. And I'm going to use that expression so I don't have to keep writing 2 pi epsilon naughts everywhere. And it's easier to write at 2 k sub E than that. Okay, so that's the electric field. And if you're going from some R initial to some R final, the change in potential in that case, delta V, would equal the integral, the negative of the integral of E dot dl. Well, E as a vector here would be, put a semicolon between those, it would be the value of E in the r hat direction, which is just going to be a unit vector pointing away from the wire. The dl that we have here, I can write it as dr in the r hat direction. I'm going the same way. And E dot dl will then equal, well, E r hat dotted with dr r hat dot r hat is 1. It's just going to equal E dr in this case. So this delta V will end up being minus the integral of E dr. And there's my expression for E. I need to pull out the parts that are constant and leave the part that depends on R in there. And, well, I'll go ahead and write them down first. Minus 2 k sub b, whoops, integral, k sub b lambda over r times dr, and I'm going to integrate from r initial to r final, and I'm going to leave them as variables, and then at the tail end I'll plug in the values and see how that works. Well, I bet you know this integral. Delta v will equal minus 2 k sub b lambda times the integral r initial to r final of dr over r. Now, when I look at this integral, I tend to just immediately leap to what it's going to be at the end, but I'll do it in steps for you here. That will equal minus 2 k sub b lambda. The integral of dr over r is the natural log of r. We'll be evaluating it at r initial and r final. And that'll give you natural log of r final minus natural log of r initial, but that's the same as the natural log of r final over r initial. So I can write this as minus 2 k sub b lambda, let's see, times the natural log of r final over r initial. Okay. Again, I'm going to get a minus sign for things if I solve for lambda at this point, but I don't know which probe on the meter is going to be correct here. And so I should actually write this as the absolute value of delta V is going to equal the absolute value of all this stuff, because I just don't know how it goes, at least with what I'm told. So anyway, let's just say that the delta V we get, it's 575 volts. And that will equal 2 k sub b lambda times that natural log of r final over r initial. And now I can solve for lambda, figure out what it is. Lambda will equal 575, and I'm going to write my volt as a joule per coulomb. Help me with this. Let's see, divided by 2 k sub e times the natural log of, in this case, our final is 3.50 centimeters. And I'll be dividing by 2.50 centimeters. Those units will divide out. Unit-wise, for trying to figure out what's going on here, on top I'm going to have joules per coulomb. On the bottom, I'm going to have the units of k sub e, which are Newton meter squared per coulomb squared. And I'm going to write that Newton meter squared as a Newton meter over coulomb per coulomb squared as a coulomb times a coulomb. And the reason I'm doing that is because a Newton meter is a joule, and this much is a joule per coulomb. Well, I've got that on the top, so I'll have 1 over meters per coulomb, which is coulombs per meter. So that's what we expect for a linear charge density. Okay, and then we can just plug in the things. And remember, k sub e is 8.99 times 10 to the 9th Newton meter squared per coulomb squared. But we'll just plug it in here. Oh, I think I already did. I think I got 9.50 times 10 to the minus 8th coulombs per meter, which you could also write as 95.0 times 10 to the minus 9th, but that would be a nano, so you could write it as that if you wanted. So it would be the same thing. Okay, now it says if you now place one probe at 3.50 centimeters from the wire and the other probe 1 centimeter farther away, will the voltmeter read 575 volts still? Well, we figured out the potential difference here. The potential difference in magnitude, at least, is going to equal 2k sub e lambda times the natural log of R final over R initial. And when we had, if we used the current distribution or the charge distribution that we figured out and plugged in the values, if they were R final was 3.5 and this was 2.5, then we would get that 575 volts. But they're basically asking, is the natural log of 3.50 centimeters over 2.50 centimeters the same as the natural log of 4.50 centimeters over 3.50 centimeters? And I'd say, no, they're not. This is 7/5. This is 9/7. And I think 7/5 is bigger than 9/7. So you can check that out on your calculator, but this isn't the same. Now, here's something funny. If you had 3.50 meters and 2.50 meters, you'd get the same potential difference. If you had 3.50 kilometers over 2.50 kilometers, you'd have the same potential difference as you have here. As long as this ratio is the same, you'll get the same potential difference. But 4.50 over 3.50 is different. Actually, I'll calculate the log of 4.5 over 3.5. Natural log, wherever it is on here. Yeah, the natural log of this is 0.251. The natural log of this is 0.336. So this is larger. This is going to be smaller. So this voltmeter in the second case will read less than 575 volts. And that's because it's a lower ratio. Okay, I think that was, oh, the last question on here. If you place both probes 3.50 centimeters from the wire, but 17.0 centimeters from each other, what will the voltmeter read? Okay, well, here's the wire. They are long, straight wire. The electric field from this thing is pointing in this direction, and you're going to put one of the probes here 3.50 centimeters away from the wire, and the other probe also 3.50 centimeters away from the wire. But remember, this is the direction of the electric field. Okay. Now, if you want to know the potential difference between these 2 points, delta V, and let's just suppose you're after the absolute value of it, so you're not going to put the minus sign on there. Or you could just imagine doing this, taking absolute values of everything. But it'll be E dot dl here. Okay. Well, as you're going from this to this, your dl is going to point in this direction. E is going to be pointing in this direction, and they will everywhere be perpendicular to each other. And so E dot dl is going to be 0 everywhere, so will its integral. So this will just be 0. And you won't have any potential difference in that case. Okay, more. Oh, I don't remember if this is the order that I had them printed off or not, but we can do this anyway. The nuclear fusion in the sun. I don't know if we talked about this fall quarter or not, but there's a three-step process of nuclear fusion that happens in the sun. And the first step is just two protons colliding together. And they fuse together to make a more massive nucleus and release energy. Oh, maybe I should do. Yeah, let's go ahead and do the sun first. And then this is nuclear fusion. And then there's another problem with nuclear fission, the splitting apart of these things. So collision of two protons fuse together to form a more massive nucleus and release energy. And somehow you have to get the protons close enough together so their surfaces are essentially in contact. And the reason for this is the strong nuclear force that will take over once those protons are close enough together has a very short range. And you actually have to get these two protons that close together before that strong nuclear force turns on and latches them together. But up until that point, they're being repulsed by their positive charge, equal positive charges. And so you're going to be increasing the electric potential energy of those two charges. Now, remember that electric potential energy U for two charges is just going to be K sub E Q1 Q2 over R squared, or no, over R, just plain R, not squared. Otherwise, it would be the electric field. And in this case, each of the charges is E, so it'll be K sub E squared over the final separation between them. Now, each of the protons has a radius of 1.2 times 10 to the minus 15th meters, and the distance between their centers is going to be 2 radii, because you'll have one here and one here, and each of them has a distance 1.2 times 10 to the minus 15th meters here. A little side note, 10 to the minus 15th meters is 10 femto, or actually this is 1 times 10 to the 10th. Well, 1.2 is what we're dealing with, but 1.2 femtometers. But when I was in grad school in physics, nobody called it a femtometer. Everyone called it a Fermi. And this is not an official International System of Units unit, but it's what everybody in nuclear physics calls it. And that's kind of in honor of Enrico Fermi, who was one of the early nuclear physicists and was active in the Manhattan Project. I don't know if you've seen the movie Oppenheimer yet, but one of the characters in there was Enrico Fermi, although I don't know that it would have been often enough where he could have known that for sure. But anyway, he was shown in there. Okay. Well, here's what we'll have. If this is a conservation of energy problem, we'll have E initial is going to equal E final. At the start, we'll have U initial, and we'll have the kinetic energy of each of these two protons that are coming in here. So you'll have 2 times 1/2 mv squared is the initial kinetic energy. So that's Ke initial. And then at the end, you're going to have U final, which is going to be this expression here, which is going to be the charge there, and they'll stop. So you won't have any more kinetic energy. Now, at the beginning, they're infinitely separated, or you can treat them that way. And so you can say this is zero as well. So the initial kinetic energy goes into the electric potential energy. So you can say that mv squared is going to equal k sub e squared over r. And what are we after in this problem here? Let's see, the same speed if the radius dot dot dot. Oh, what's the minimum speed that will allow fusion to occur? Okay, well, this minimum speed is when they're slowing down, slowing down, slowing down as they approach each other, and just as their speed comes to zero, their surfaces touch and the strong nuclear force takes over. So that would be the minimum speed. You could have them hit with more speed, and as long as that speed they hit with isn't too great, they'll actually stick together. But it's possible to have the speed be so high that they would kind of bounce off of each other too. So, but we're not interested in that. Anyway, let's figure out V. V is going to equal, I'm going to divide both sides by m and take the square root, and I'll have k sub e squared over mr. And so let's figure out what that speed has to be. K sub e, 8.99 times 10 to the 9th. Let's see, Newton meter squared per coulomb squared times e squared, which is 1.60 times 10 to the minus 19th coulombs, and I have to square that, and divided by the mass of these things, which are, they're protons. Okay, they have a mass of 1.67 times 10 to the minus 27th kilograms. You would have had to look this up, unfortunately. And then they're separated by 2.4, 2 radii. So 2.4 times 10 to the minus 15th meters. Okay, what's going to happen to the units here? Well, one thing that's going to happen is that these coulombs squared will divide with those coulombs squared. So I'll have Newton meter squared over kilogram meters. And what's a Newton? Let's see, Newton meter squared over kilogram meters. Newton is a kilogram meter per second squared, and I'm multiplying by meters squared, and I'm dividing by kilogram meters. Oh, okay. Those will divide with those, and I'll have meters squared per second squared, but I'm taking a square root, so I get meters per second. It's always a relief when I've convinced myself that the units are correct, so I didn't screw up that part at least. I've got the right ratios. Anyway. I should probably try to estimate this before I actually punch it in. Well, I'll hit enter on my calculator. Let's see, this would be about 10 to the 10th. This would be about 2 point something times 10 to the minus 38th, but I'm dividing by something times 10 to the minus 27th and 10 to the minus 15th. Okay. So I'm not sure exactly what, but we'll just see what happens here. I get 7.58 times 10 to the 6th meters per second, which seems reasonable. They're going to have to be going pretty fast. Okay, that's step one in the fusion process in the sun. And step two involves a collision between two helium nuclei, each of which has 2.99 times the mass of the proton. Okay, what in the world? Why is it 2.99 times the mass of the proton? Isn't helium 4 times the mass of the proton, 2 protons and 2 neutrons? Well, this isn't helium-4, it's helium-3. Let me show you the first step in the fusion of the sun. It's proton plus proton goes to form a, actually it forms a hydrogen 2 nucleus plus a positron comes popping out of there, plus a neutrino comes out of that reaction as well. Okay, so you took 2 positive charges, you end up with 2 positive charges. This hydrogen has a proton in the nucleus, which is a positive charge, but this positron carries away an equal amount of positive charge. So charge is conserved and everybody's happy. Then later, you will have a proton run into this hydrogen nucleus, which it, by the way, is called deuterium, but it's just hydrogen 2 is what it is. So it runs into this, and this time the proton actually sticks in the nucleus without kicking out a positron, and this forms helium-3, which has 2 protons and 1 neutron. And so that's what we're talking about here. And then later, 2 helium-3s combine, and they end up 2He1 plus 3,2He1, and they combine to form 1 helium-4 nucleus, which is that, plus 2 protons get kicked out of that reaction when that occurs. And this is the 3-step process for fusion in the sun. But we're looking at this is step 3 here. So how fast what does the temperature have to be to let those things run into each other? And actually we're told what minimum speed is required for this fusion reaction to take place if the nuclei must approach to a center-to-center distance of 3.5 times 10 to the minus 15th meters. Well, on the previous page, we kind of did all the math for this thing. We had that mv squared has to equal k sub e squared over r, and they told us what r is in this case. So let's just go ahead and use that and see what we get. mv squared is going to equal k sub e times e squared times e squared over r. And in this case, they told us what that has to be. So the v is going to have to equal the square root of k sub e squared. Oops, it's not e squared this time. It's 2e squared, because each of these has a charge twice that of the the proton. Okay, over m times r. So plugging the numbers into this scary expression, I would have a nice long mess here, but 8.99 times 10 to the 9th Newton meters squared per Coulomb squared times. When I square this, I'll get a 4 here, so I'm just going to write that there. And then I'll have 1.60 times 10 to the minus 19th coulombs, which gets squared. And then I divide by the mass of these things. This will be 2.99 times the mass of a proton. So 1.67 times 10 to the minus 27th kilograms. And then times this new R, which is 3.5 Fermi, or femtometers, or times 10 to the minus 15th meters. Okay. That's not there. That's part of something else. Okay, 8.99. Whoops, I need a square root. Oh, plus I'm going to get my other calculator. I like it better. And what do we have for the other speed? 7.58 times 10 to the 6th. For this one, I have 7.26 times 10 to the 6th meters per second. So not that different, actually. And actually, what changed, we had a 4 over a 2.99 on this one. And oh, we also had a different distance here. So this was somewhat different. But actually, by the time you factor this in, I think the ratio ends up being pretty darn close to 1. So not that different a speed. Okay, there's a third part to this. We studied thermodynamics. We learned that the average translational kinetic energy of a particle with mass m in a gas at absolute temperature T is, there's supposed to be a 3/2 on here. Let's see, I think that should be, if you print it off, or if you print off this file yourself, it will be in there. But this is one of those things where when I went to the new formula or format, yeah, it's 3/2 KT. So this is what the expression should be, that our 1/2 mv squared will equal 3/2 k sub bt. That's Boltzmann's constant now. And so we have to be careful with that. But we want to know how much temperature is required for this to happen. Well, we didn't actually calculate the kinetic energy, but we did calculate the speed, and we know the mass. So we can solve for this. T will equal 1/2 mv squared over 3/2 k sub b, which will end up equaling, let's see, the 2's go away, and I'll have mv squared over 3 case of B. So let's do this for the protons. And let's see, that's 1.67 times 10 to the minus 27th kilograms times that speed we figured out for the protons, wherever I put them. 7.58 times 10 to the 6th meters per second. And that has to be squared. And then 3 times case B. And I think when I do it, this is for the protons. When I do it for the helium nuclei, I may be able to just change a couple of numbers in the numerator of this. Well, I'll have to put a 2.99 times that. Oh, well, 3. Boltzmann's constant. All right. 1.38 times 10 to the minus 23rd joules per Kelvin, I think. Yes. Okay. Joules per Kelvin. Now, we're going to have joules on top. We've got a kilogram. We've got meters squared per second squared. That's a joule. So the joules divide out, and I've got 1 over Kelvin on the bottom, which flips up, and I'll have a temperature in Kelvin. So the temperature needed for the proton fusion, let's see, is rats. Won't be able to quite finish this or do the other problem. I may record an extra video somewhere along the line and do that, but minus 27. Okay, I get a temperature of something like 2.32 times 10 to the 9th Kelvin. Does that make sense? That'd be, let's see, 5 times 10 to the 13th. 5 times that, it's going to be around 8 times 10 to the minus 14 by that. Yeah, makes sense. This says temperature is about 1.5 times 10 to the 7th Kelvin. This is like 15 million Kelvin. This is 2.3 billion Kelvin. So how does that compare? How can the reactions occur under these circumstances? Well, this is the expression for the average kinetic energy of a particle. And you remember when we studied thermodynamics, the actual particle speeds have this curve where some fraction of the particles are moving much faster than this speed. So that's part of it, that you don't have to have the average particle, which is down here somewhere doing it. You can have the ones that are way out at the extreme end of this thing doing it. And so that's part of it. And then another part is that at this level, when you're starting to consider fusion between subatomic particles or nuclei, actually, that quantum mechanics comes into play. And so things aren't quite as simple as we've been treating them. So, but still, this is a really high temperature, and that's about the minimum temperature needed. Actually, I think around 10 million Kelvin is needed for that to occur. But it's collisions between the most energetic of the particles that are in there, of the protons that are going on. And right now, the material in the core of the sun is plasma, and you've got free protons running around loose, free electrons running around loose, and then some fraction of helium is in there as well, the helium that's been formed, and then the helium-4 and helium-3 are in there as well. So, okay, we'll have to stop there. And I put up a survey for a meeting tonight, and I've only, well, if I reload, I don't know how many people have responded to it tonight, but I can't start until 7:30, but it looks like of the 3 people or 2 people who've responded, 2 of them can make any time after 7:30 or later. So I'll let you know later when I've had a chance to look at more of those, just when we'll meet. So stop recording here and find my cursor. There it is.